Welcome to this practical session on artificial neural networks. We should start by importing NumPy, matplotlib, and pkbar, which will be used in tracing losses, accuracy during training, and then pandas for treating the dataset. Firstly, we shall define this linear class, which inherits some of its properties from the class layer. Now, it's important to note that in a neural network, we could have different types of layers. And one of this type of layer is a linear layer, which we are about to define explicitly. We have a constructor which takes as inputs the input or the number of features in our input to the linear layer and the number of features in the output of the linear layer. So we could term this as stat and end. So this is the stat and then the end of the linear layer. From here we could create a tensor or an array which will be used to create parameters. Now these parameters will be the weights, the biases, the partial derivatives of the loss with respect to these parameters, and the partial derivative of the loss with respect to the bias parameters. Now we should get back to this, but for now let's work on the backward and then the forward pass of a linear layer. Notice that with the backward pass, we take as input d and x. And then from here we return d times theta transpose. In this case, we are using this add, since multiplication of matrices in Python can be done basically with this add sign. So we have d times theta, which is this transpose. Now, how is this theta? Recall that we had defined this parameters. So we have this parameters dot weights. So basically theta is the weights transpose. So we have d times theta transpose. And then for the gradients, that is the partial derivatives of the loss with respect to the different weights, we have this self.parameters.gradients, which is x transpose times d, as we had seen in the slides. Now coming back to the slides, suppose we are trying to find the partial derivatives of the loss with respect to, say, these parameters. Here we have 1, 2, 3, 4 inputs and 1, 2 outputs. So we have a stat of 4 elements and an end of 2 elements. And then we find the partial derivatives with respect to this thetas as x transpose d, as we've just seen in the code. And then to obtain d, we use the d which was previously given to us from this other linear layer. Now that we've gotten d and we've used it to find this partial derivative, we'll calculate d such that the d we use here is going to be used in this other linear layer. So we've seen this already where we back propagate this error d, and that's why the output in the code is this d, such that it could be used in the next layer. Now for the biases, it's quite simple, as we just have an input which is equals 1. But since we're doing training, we have many data points to train on at a time. We actually have this np.1s to signify, say we have a data set of 5 points, so we'll have 1, 1, 1, 1, 1 to say that we are training on all these 5 points at a time. But if we had to work with just one of these, we just have this 1. So in that case, we just have this x.shape giving us 1, since basically x.shape 0 of index 0 is giving us the number of elements in our data set. So if you have this to be 1, we just have your 1, and basically we just have a 1. Now that we can have many more elements in our data set, we could leave it like this, such that we could have many more 1s. So if we have, as we saw, 5 data set or a 5 data points data set, we'll just have the 1, 1, 1. So there we go. And then similarly for the gradients, because we've calculated the gradients for the weights And now for the bias gradient, we have the same formula where we have X bias transpose times D. So let's take this off. Okay. Now for the forward pass, we have our start features and our end features. So we take this as our input, and then we output the end features. Recall that we have first of all a forward pass, and then we go backwards. So for the forward pass of a single linear layer, we just have X times theta plus the bias. So in this case, we just have X theta plus the bias, which is just a simple linear model as we've seen previously. Also notice how the dimensions of this matrix, which is parameters dot weights, depends on the number of inputs and the number of outputs. So these are just basically numbers. We could take, like in this case where we have this 4 inputs and 2 outputs. Here we're gonna have 4 and 2. So here we have 4, 2 as inputs and output. So we'll just take this and replace right here. And this means we're going to be creating a tensor or an array which is of dimension 4 by 2. And then when creating these parameters, the parameters dot weights array is going to be a 4 by 2 matrix, which is going to contain all the weights theta. So let's go back. As earlier discussed, the whole point of automatic differentiation is to get, say, a function like this and create a computational graph from it. So basically we're able to form this graph from this function. Now replicating this with artificial neural networks, we want to create, say, this linear layer, this other linear layer, this linear layer, this other one, and then link them up. And that is why we create this layer class. So we have this class layer, which we create to represent the different parts of the computational graph. In this case, since we are mostly dealing with a linear layer with the kind of artificial neural networks we are working with for now, we've defined a linear layer already. But then we could have many other types of layers, like conv layers, recurrent layers, and even other custom layers which you may want to define. So in that case, we want that this layer is going to be a template for any other layer which is to be created. So that's why we had this linear layer which inherited some properties from the class layer. Now with this class layer, basically what we have is the parameters, as each class or each layer has its parameters. And then we are able to initialize these parameters from start before training. So like in this case, where we get a tensor, or from here where we had this tensor which depends on this inputs and outputs, and we have seen exactly how this works. Then we have this init param function which takes in the tensor. With this init param function which takes in the tensor, we're able to create parameters. So from here we have this object param of the class parameter. Now this class parameter is one whose task is just to store the parameters of a given layer. In this case, we are working with a linear layer, so we have this class parameter which stores the weights, the gradients of the weights, the biases, and the gradients of the biases. And as we had defined previously, in this case, we have this tensor. Suppose we have 4 input and 2 output, so we have this random 4 by 2 tensor, which makes up the weights, and its gradients are initialized to zeros. We have a 0 like of the weights, and the bias initialized to zeros, and then the bias gradients is 0 like of the bias. Now the reason why we have this tensor.shape -1 or tensor.shape index -1 as we've had here is simply because once we have our weights, or rather when we are in a linear layer, the bias depends actually on the output and not the input. So getting this shape here, this index -1 will give me the number of outputs, which in this case, for example, is 2. So here we're going to create this bias with a value of 2 this way. Now this zeros get 0 like this. So here we have 2. So it means we're gonna have something like this, 0. And if we come back here, we'll understand why we needed those 2, because for this bias we just have this theta double prime 0 1 and then theta double prime 0 2, since we just have 2 outputs. After initializing the layer, another very common operation on all layers is the update. So we're going to use an optimizer to update these parameters, and we shall see later how to define these optimizers. So with this, it means we could define the SGD, we could define momentum, ADAM, and many others. So if we define our SGD, we could have our constructor, which takes in the learning rate, and note that we could have many other parameters like rho, epsilon, or whatever parameter depending on the optimizer. But since with SGD we just need the learning rate, that's why we have this, and we say by default our learning rate is 0.1. Now the update is what we know already. So we have the parameter weights, which is basically theta is equals theta minus the learning rate times the partial derivative of the loss with respect to theta, and similar step is done for the bias. So all we do here is to pass in the parameters as we had seen previously here. So with this optimizer, we get the optimizer, we update it using the parameters of the layer, which in this case is a linear layer. Our next step will be to define other layers like the sigmoid layer and even the softmax layer. So let's look at the sigmoid layer. Notice that we have these parameters defined as known, and since the sigmoid layer doesn't have parameters, we're never going to modify this value for the parameters. And then we have the backward and the forward pass as we had seen with this linear layer. With the forward pass, we have the function we know for sigmoid, 1 divided by 1 plus e to the negative x. And then for the backward pass, we have the derivative of this sigmoid function with respect to the futures x. So in this case, we have d times, or rather we have s times into 1 minus s. And it's actually this value d times this, which is passed to the next layer. So we propagate this loss to the next layer. It is exactly for this reason that we modify this d from d theta transpose to d theta transpose times the partial derivative of a with respect to the futures x. And that's, in this case, we just have s into 1 minus s. Or to conform with this writings, a into 1 minus a. So right here, this represents the partial derivative of a with respect to x we have seen previously. And then here we have the d, which was propagated from the layer right in front of the sigmoid layer. For the softmax function, we had defined this operation previously. Now, so for the forward, we just have this softmax function, which is called, and then for the backward, all we do is we just take the d, which we get from the loss, and then back propagate it to the next layer. We shall also work on two other activation functions, that's the tanh and the ReLU. They are also seen as layers as the sigmoid and softmax layers. So here we have this tanh. The forward is simply np.tanh of x, so we'll calculate np.tanh of x for the forward, and then the backward is 1 minus tanh squared. So we had seen this already in the slides. Now for the ReLU layer, we have the forward being np the maximum between 0 and x. So if we have an input x, let's take this up. Let's take this from here. So we have this. Say we have x equals np.array, and then we have this -1, 2, say 0. With this, let's print out the output from here. So from here we see clearly how all negative values are sent to 0, and all positive values are maintained, hence the ReLU. And for its derivative, all negative values will be sent to 0 and all positive values to 1. So from here we could do this. Let's print this out. Print this out. And there we go. So that's our ReLU function. Let's save this. Now that we've done this, we're ready to look at the models. So it's important to note that in the creation of this mini artificial neural network library, we have layers and models. For a layer, it just could be just this linear layer, it could be a sigmoid layer, softmax layer, ReLU or tanh layer. Whereas a model regroups several of these layers. So in this case, we'll call all this network our model, and each of these will be the layers. Let's look at the code for the model. We have this constructor which gives us this computational graph property. Now basically computational graph is a list made of the different layers which will constitute our model. Then we have this add method. This method basically takes a layer and then adds it to this computational graph. So here we have computational graph that append layer. Because computational graph is a list, we could use this append function. So coming back to the slides, for this first layer, we're going to append it. For the next layer, which is the activation function, we're going to append it. For the next layer, linear append, next activation, next linear, next activation, next linear, and finally the activation. After appending these layers, we have to compile the model. Now compiling simply means we are giving it some of its properties which we use during training. Now during training we need a loss function and also we need an optimizer. So it's important that we define this before training. And then for the model we have this forward pass. This forward pass actually goes through the whole model. So that's why here we have for layer in the computational graph. So we're going through the whole computational graph. And what we do simply here is we go through the layer.forward. So if you come back, if you could look back for sigmoid, basically what we are doing is going through this method. For this other, for the linear class, we have this forward method which we defined already. And for the others, we have their different forward methods. So depending on the layer with which we are working, we simply do this layer.forward. And that's how moving through this computational graph, we have an output y. Now, what's the use of this y_int list variable which we've declared, which is actually a list? If you recall from this formula, to find the partial derivative of the loss with respect to a given theta, we needed its x previous and it's d after. So that's basically we needed x start and then it's d end. So that's what gave us x transpose d. So what does this mean? It means when going through the back pass, we need the values for x and the values for d. And so that's why when going through this forward pass, every time we have a result, we store it in a list, y_int list, such that during the back pass, we'll collect that value or those values from y_int list and do the computation for the partial derivative of the loss with respect to theta. So that's why we have it here like this. So y_int list, it gets the y. So initially y is x, it gets the y. So for this, for a particular layer, we append its output to this y_int list while we keep on moving forward in the layers. At the end of the day, we're gonna have this y, which is the output of the whole model. Y_int list, we get the output for each layer and it's gonna be stored such that we could use it for the backward pass. We could move now to the fit. Let's look at the fit before looking at the fit bash. So for the fit function, what we're doing here is basically gradient descent, and we have seen this previously. Now if you notice, we added this p bar, we use the pk bar model. Now basically this model will help us in tracing the loss values as we go through the several epochs, and this is very helpful as it helps us follow the training of our algorithm very easily. So what we've defined here is this PK bar. We've given it a name. So when training is gonna start with this training, we have our target, which is epochs. So basically this is the number of epochs. That's our target. And then for epoch in this range, what we do is we feed a batch. So we take a batch. We had discussed this earlier already. So we have this. We take a given batch and we feed a batch. So this is the feed method, and then this is the feed batch method, which is called in a batch in the feed method. So we feed a batch. We take in X. That's the batch. So we taking a given input batch and an output batch, and we pass it into the feed batch method. Now let's take a close look at the feed batch method. With the feed batch method, what we're doing is we're going through this forward. So we have defined forward already. We'll go through the whole model, and we have an output where we've kept the intermediary outputs for each layer. And then we go to calculate the loss. So depending on the loss function we've defined, we have the output from the model and we have the target output. We calculate this loss. Then D is the A minus Y we had calculated earlier. So D is actually equals A minus Y, where this A is the predicted output and then Y is the target output. So looking at the slides, our D is this ym minus ym prime. And then what we do next is we go through the computational graph and then the y-int list simultaneously and extract y-int and then the layer from the computational graph. Now we're doing the backward pass, so we go from the output to the input, so we're moving backward. Then we compute D, which is layout of backward. So for each of the layers, we'll simply go backward. So if it's a linear layer, we're gonna go backward. Let's look at it from the function we had defined previously. So in this case, we're gonna use D, which we got already, which was ym minus ym prime. It's gonna be inputted here, and then based on these, we're gonna compute now D 3, for example, just as we had here, because from D initial, that's the D4, we had this, and then to have D3, now we're gonna compute D4 times theta trans, and that's exactly what we output right here, and that's what the next backward pass is gonna take as inputs. Now that said, we could come back to our feed function. We have this layer the backward, which not only outputs the D for us to use in the next layer, but also gives us a value for the partial derivative of the loss with respect to theta. So when doing this backward pass or this backward or applying this backward function, we have this partial derivative of the loss with respect to theta, which is given as a parameter as a gradients, which is now x transpose times D, and would repeat same for the bias. From this, we could look at the next step. We've done the backward step. We've computed the partial derivative of the loss with respect to the different weights and biases, and then we update the parameters. So for this particular layer, so what we do here is if this layer, the parameters is not known, so we're supposing that we are working maybe with a linear layer. So if you have sigmoid, you have softmax, you have whatever, or tang, whatever activation function layer, we don't actually get into this. So yes, only for layers like linear layer, conv layer, or any other layer which has parameters. So with this now, we update our parameters using this optimizer, and after calling this update function. Now recall that we had defined this function earlier on the layer. So here we had defined this update function as a layer, since all our layers could have updates. And then we had also seen how we updated this with this optimizer, for example. So now we have seen how we completely have taken our weights, we've updated them, and then we return the loss. So for each epoch, we're able to return the loss depending on the model parameters we have at hand. And then this feed is repeated for the different epochs. So for the number of epochs we work with, we're gonna repeat this feed batch and then compute the loss for a specific epoch. Also, we update this bar. So basically this PK bar module will help us print out the loss at a particular instance and also tell us how far we've gone with training. With all this put in place, we are ready to make use of this our mini library, which we use when training our models. So here we've defined X. Now we're working with the XOR gate. So we have 0, 0, which gives 0, 1, 1, which gives 0, 0, 1, 1, 1, 0, 1. So this is our data set. We're going to see how this XOR gate is going to be represented by our model. We have number of epochs defined. We have the model defined, that is the model object created from this model class. We add this layer to our model. Obviously this goes into the competition graph. We add this other layer, we add this other layer, and we finally add this layer. Now since we have just one output to be classified whether it's a 0 or a 1, we have binary cost entropy loss. So here we should change this to a BCE loss instead of CCE. So here we have BCE loss, and our output here is a sigmoid instead of a softmax. Now our SGD, we define a learning rate of say 0.5. Then for the losses of we call this feed function from model, we have the inputs X, we have Y, we have the number of epochs which we've defined already. Then we have the batch size. In this case, the batch size is going to be 4, since x.shape of index 0 is 4. And then from there we could plot. So let's run this and see what it gives us. So we see exactly how this works. We see that as we're training, the PK bar model permits us to see how far we've gone, the loss at a particular instance, and the number of epochs we've gone. After this, we're able to plot. Since we've been accumulating the losses as we've been training all through the epochs, we have been accumulating these losses by doing this. So after, when we output these losses, we get it from here through this model.fit. We take these losses, and that's exactly what we print out. So we see how this gives us a loss of 0.04. Now this is a model with two hidden units. That is, we have this linear, we have this other linear. Now let's work with just one. So suppose we have this, take this off, and then we go our input 2 and this. So if you notice, this actually happens to be a simple logistic regression model, since we just have all the input and then we have the output. And if we decide to train this, let's take this off. We see that after training, it doesn't cross 0.6933. We could even increase the number of epochs to 100. We'll see how this PK bar helps us actually follow our training throughout. But nonetheless, at the end of training, we still don't cross the 0.6932. Our next step will be to work with a different data set. That's a data set we're working already with. Here we run this letter recognition data set while taking this off. So we could just simply comment this. So after running this, we'll try to run this directly. See that we have an error, and that's because here our input is made of 17 different units. So here we should take this as 17, and then here, for example, 26. So running this, we already have some problems of divergence. Kernel, we interrupt the kernel. Let's take this to say 3. Still that problem, we interrupt the kernel. Let's take it to 5. Interrupt. And then we'll notice that the error we've been making so far is we've been working with the output, which is sigmoid. So we should have a softmax output here, since we have a multi-class problem to solve. So if we change this to softmax, let's take this back to say 3. Here we have the CCE. Instead, we run this, interrupt, take this to 5, Again, we keep on having these errors. Let's interrupt this. Now we're checking again on this. We see that the loss we've been dealing with is the BCE loss. That's the binary cross entropy loss. So if we turn this to CCE loss, we run this, and we see that it starts working fine. So the problems we had was we were working with a sigmoid. Yeah, we were working with a BCE loss instead of CCE loss. That's why it was hard for it to actually start converging. So with this, let's take a smaller value here, interrupt, or rather a bigger value. Now let's go back to 4. This still diverges. Okay, so at this it actually works fine. Now if we could go back to our previous code on the multi-class classification and run this for 20,000 epochs. So we're running with the same data set, the same letter recognition data set for 20,000 epochs. We have this loss which doesn't cross the 0.80 mark. So we'll see that it actually converges, and this is the smallest loss we could obtain. So this tells us already that with this softmax model we are having here, since we just have this one linear layer with a softmax output, we are never going to cross the 0.8 loss mark. So our loss is never going to be less than 0.8. So what we could do here to ameliorate the performance of this model is by increasing the number of linear layers, so by stacking more linear layers together. So we could do this. We have this. We have model.add sigmoid. So obviously you could play around with this code, add relu, add tanh, and see how it works. For now, we just work with the sigmoid activation unit. Take this to say 300, this to 300, and then here we go. We have our output. So we'll take this to 20,000 epochs as we did for the softmax regression problem or the softmax classification problem, and then compare the results with respect to the loss. And then next time we shall look at the performance test. We're going to evaluate the accuracies. So for now, let's run this and see how it trains. Nonetheless, we could see how maybe increasing this will help us speed with our calculations, but this actually diverges. So as it begins to diverge, we could take, for example, 5, take this to be 3. Okay, running this, it starts to converge, so we'll have to wait for a while. Then after going through 20,000 epochs, we have a loss of 0.09, which is way below the 0.80 mark we weren't able to cross when working with the softmax regression model. This shows how powerful artificial neural networks are when it comes to understanding very complex data sets. And this wouldn't have been possible without the computationally efficient backpropagation algorithm.